Okay. Hopefully be able to hear me. I hope. So again, this is going to be the lab portion, and is a place where you again could get help on the lab. So again, this is a good time to go try to watch the video, start working through it. Also, obviously, you can ask me any questions that you like during this time about anything. It doesn't necessarily have to be about the lab. Again, probably the best way to do that is still type it through the chat. That way we're not all talking over each other. And again, if you want to send it more private just to me, you can, and I'll respond, type back to you. Also, I just asked us like before, a reminder, these are also being recorded. And if you could keep your videos off as well. Again, I just don't have 100 boxes up here. So really at this point, unless there's something specific that we need to talk about in terms of the lab component, I will again just kind of be here like I would be sitting there in the front of the room. You could come up and ask me questions if you need to ask your questions. And again, we're going to keep these separate from the lecture ones. That way, in case there's something of importance we need to kind of record and post, we could, and they're separate from the lecture recordings and stuff like that. So each day, Monday and Wednesday, you will have two different links. Again, one for the lecture like we did before, and then obviously one for the lab component. So just a reminder, again, the lab could be found on that modules page with the link to experiment, I believe is 14 for today. That should actually embed the video as I showed you earlier in Canvas, and you could actually watch it from Canvas if you like. I suppose you could go to YouTube and watch it as well from the link. And then again, after you watch it, you should be able to fill out completely the experiment for that day. So you can fill out the data table, the post-lab questions if there was post-lab questions. In this case, there's not. And then when you're done with all that and you filled it out, again, you need to sort of scan it in, either using perhaps a phone app might be the easiest nowadays. And again, I believe somebody sent around Adobe Scan has a free app that will let you basically just use your phone's camera and kind of scan it in to a PDF file, which might make it easier for everybody to do. Or again, if you happen to have a scanner or some other program that lets you do that, I'm not tied to Adobe Scan or anything like that. But you'll need to, again, save it. And then when you do save the file, you may just want to just be sure nothing gets sort of mixed up or anything like that. I don't think it will. But maybe in the file name, you might want to include like your last name or something. So, and sort of what it is, like, experiment 14 and your last name. That way, at least it's associated when I see the file. It should save them all obviously individually for you, but that might be a good secondary sort of approach in terms of how to save those files. So again, I don't really have anything I'm going to particularly talk about or lecture about other than answer questions in regards to, at this point for today, the class, if you have questions about that, are the actual experiment 14. Again, a reminder that it is due this time, experiment 14, on Wednesday by 12 o'clock is when you have to submit it. And most of the experiments will be due probably within the day or so of when it technically we're doing it. And a reminder that all the experiments you'll be able to find links up online. Yeah, so there was a question about, for this particular one, the evidence of reaction portion. Yeah, you should write from the video as you're watching it, what you actually see. So some of the video I think is sort of live action, if you will, and some of it I think is more like PowerPoint sort of slides. But they both will show you some sort of observations like, hey, you see bubbles, it turned yellow, it got cloudy, So definitely in that portion of today's experiment where it says evidence of reaction, That's what you're looking for. So as we talked about with chemical reactions, evidence of chemical reactions are things like bubbles, which indicate gases were formed, a solid is formed, which is a precipitate, fire, for example. So those are all sort of evidence of chemical reactions that took place. So 2 questions for the evidence one. Uh, for the evidence of a reaction, again, I'm not looking for a long sort of description on that or anything like that, but you just need to kind of describe what you see, and for the balance equation part in the reaction table, if you want to write aqueous or solid, you don't necessarily have to at this point, but it does need to be balanced. So make sure that those equations are balanced. They have the proper coefficients and stuff like that. I don't recall off the top of my head. I'm not sure I don't think you'll necessarily have to include the states. You can if you like on this one, but definitely the equations do have to be balanced. Yeah, so Grace, for this one, it is just the molecular equation. So I think there's a lab coming up where you'll do all the net ionic equations and stuff like that. But for this particular one, it's just write the balanced reaction for each of the equations that you see. Jack, in terms of evidence of reactions, again, things like bubbles for gases, solids being formed, colors and stuff like that, fire, those are all evidence of reactions. Yeah, Thomas, there was a pre-lab. Expired at like noon today, but I forgot to extend it. So I'm going to extend it after I'm done here during lab time. So later today, I'll be back up there and you'll have until like Wednesday to do it if you missed it for today. And again, in the future, there'll be pre-labs for all the labs that we normally would have done in person. They'll be due again on the day of the experiment by 12 o'clock. So I forgot to do it with everything that was going on. I'm going to extend again the pre-lab for today because I know probably a lot of people maybe missed it. One more time. So let me just take a look here. Okay, so your question was about part B, I believe. So in part B, take a real quick look here. Oops, too far. Come back. Part B was with the water and the battery. Yeah. So yeah, part B, hydrogen gas and oxygen gas is being created. So it's a type of reaction that's known as a decomposition, where basically you start with one thing and you break it apart into two things, two or more things. So let's go back here. So for example, on that particular one, you're basically taking water and you're basically going to break it back into hydrogen gas and oxygen gas. And that's all the bubbles that you see basically that are forming there. So Grace, let's see. You're on the right track there, but let's just go here. So remember that when you put something like magnesium, when it creates a charge, it has a +2 charge, and oxygen, when it creates a charge, has a -2 charge. So when those guys come together, you just need one of each in terms of on your product side. You know? That would be the solid that you saw in that video. Yeah, so remember that when you go to balance the equation, it's only the coefficients that you should change. And so, for example, there, remember that only the numbers in front should be changed. So if you needed the 2 for this guy, you actually would want to put the 2 there and then finish balancing the rest of it. Because obviously when you would do that, that would change the magnesium, which then would also need a number here. It should be a 2 as well. Yeah, you wouldn't write O2 on this side again, because at that point, these two came together and they formed that magnesium oxide, which in the video, if I'm not mistaken, I don't know how much they showed, I can't remember, but it's kind of like a white powder that's usually formed when you do that reaction. And that's the magnesium, the oxygen coming together to make kind of that solid. You would have the O2 on this side, on the left-hand side, because it's still a gas. So you would still have the O2 there. Yeah, so Eric, it looks good. If they took silver nitrate and reacted it with copper, again, what's going to happen really in that case is right over here, the silver nitrate and the copper. Again, if you saw a reaction, the copper is going to kick out that silver nitrate, and when it does, the silver will be by itself with no charge, and the copper would come together. In this case, I don't know if they explained it, but usually it will be copper 2. So that is sort of how you would get to that there. You probably wouldn't know that unless they kind of told you. But the copper, when it does get a charge on this side, will end up being a +2 charge, which is why you would actually need 2 of those nitrates. So this is a type of reaction, Grace, that we haven't got to yet. It's in the chapter where we're at. We're almost getting there. But this type of reaction is what's known as a single replacement reaction. And what happens is because this is really a positive guy and a negative guy. Although at this point right here, copper has no charge. Let me kind of flip some different color here. So copper has no charge here, but when it normally does have a charge, it normally will make a positive charge. So in a single replacement reaction, what happens is the copper will kick out the positive guy. And what that creates then is when he does that, this copper becomes positively charged. And that's how it hooks up with the nitrate that's negatively charged on this side. And the silver goes from something with a positive charge to something with no charge over there. It's basically just solid silver. And this was a type of reaction that's known as a single replacement reaction. Basically, if it's a positive guy, it comes in and kicks out the positive guy. If it's a negative guy, it would kick out the negative guy. So those reactions, single replacement reactions, are very similar to what we did in that experiment with those halogens and the test tubes and the hexane. Um, in order for this reaction to occur, the copper has to be more reactive in this case than the silver. Otherwise, this reaction would not occur. So again, because it doesn't have a charge here, but when it normally does, it would be positive. It will kick out the positive guy. So again, in the observations table, you should write the actual observations that you see. So maybe you saw bubbles, maybe you saw precipitate form, yellow precipitate, green, whatever color it may be. In the actual reaction table, which is at the end of the experiment, you actually need to write the balanced equation. So um, for example, like up here, it is not balanced. You need to put the numbers in front to balance it, but that's sort of what you're looking at. So for example, this guy, if you did balance it, you would need a 2 there and like a 2 there. So something like this, much neater, obviously, would go in the reaction table. While in the observation table, it would just be what you actually observed from the video as you're watching it. Zach, I probably will post these as well if you guys think it will be helpful to kind of see some of this stuff. I'll probably post them as well, unless there's a lab day when there's not much going on. But I'll probably post them in case you want to see and hear what I was scribbling on, if you think it'll be helpful. I'm sorry, Zach. The lab recorders were there. The chats won't be. The chats actually don't get uploaded and recorded with it. It will just be what you see on the screen. So that's why I'll try to repeat the questions that I hear in the chat. That way you can hear them or see them as well. So Grace, you do need the 2 waters up here because that will get you the 4 hydrogens that you need. and that'll also get you the 2 oxygens that you need to balance out over there on the other side. Without the 2 in front of the water, you would just have 2 hydrogens on the left and 1 oxygen. So again, in terms of the magnesium one here, when we do put magnesium, when it does gain a charge, it doesn't have a charge to begin with, but it does gain a +2 charge. The oxygen from oxygen gas also, when it gains a charge, has a -2 charge. So actually you would form MgO on the right-hand side. And remember, to balance it, what we want to do is actually, again, put a numbered front. So we need to put the 2 in front there to balance it. Yeah, Andrea, to figure out the charges, again, things will make their normal charge. So remember that on, for example, when we look at the periodic table here, everybody in group 1, right, is +1. Everybody in group 2 is +2. Skipping the transition metal, I'll make it really small there. Going to group 3 is going to be +3. And again, that's going to be pretty much your aluminum. Group 4, no real good pattern. Group 5, -3 will be our nonmetals. Group 6 will be -2. And group 7 will be -1. Again, the only transition metals that have fixed charges as well is silver will always be +1. Zinc will always be +2. And cadmium will also be +2. So these are things with sort of fixed charges. When you look at it, everybody else, you sort of has to figure out the charge based on what it's bound to, but those are what you could use to sort of figure out those charges. The same thing that we use for nomenclature and when we were talking about it. And again, a reminder that those transition metals can make multiple types of charges, so they can have variable types of charges. So Grace, that also is another single replacement reaction. So I'm just going to flip to kind of a clean page. Just kind of write on that. So I'm assuming from what you typed there, they were taking hydrochloric acid and reacting it with magnesium, I think is what you had there. If I'm not mistaken. Yeah. So this is also very much like a single replacement reaction. So hydrochloric acid, as we sort of talked about a little bit today, acids basically plus and negative. So it's really like an ionic compound. So magnesium, although it does not have a charge there, will come in and basically kick out the positive guy. And that's because magnesium here normally will make a positive charge. When it does, the hydrogen comes out by itself and it comes out as hydrogen gas, which means you should have saw some bubbles there in that video. And then what ends up happening at that point is the magnesium will now gain a +2 charge and our chloride is still -1. So these guys will come together and make our other product, which is again magnesium chloride. Again, we need 2 of these to balance out the charge to get us there. And that's what it will look like. So usually in this type of reaction, when you do a single replacement, you can move a hydroxide bubbles. So I think we might have done some experiments earlier on where you had to put like your finger over the test tube and then it kind of barked at you when you put the splints near it. That was sort of the same idea. So anything that has hydrogen involved and it's a single replacement reaction where it gets kicked out will typically generate that hydrogen gas. And those are the bubbles that you see. Obviously, what I wrote up there is not balanced, so you need to make sure you balance it. If that's the same one that's up here, this would be the equation with the correct sort of products. It's not balanced, so you do need to go back and put some coefficients in there. So again, a reminder that to balance the equation, you got to make sure that you go back after you get all the right formulas. And that's the key here. You want to make sure you start out with all the right formulas, and you want to then go back and put numbers in front of each of these to make sure you have the same number of elements on each side. So very common when people are doing things like you're doing in this lab, and they have to sort of predict what's on the product side. They'll try to predict and balance at the same time, and they'll end up getting the wrong formulas and things won't balance. So when you have to write the products from just the reactants, always start with just the right uh, formula, get everything in the right formula, and then go back and put the numbers in front to balance. There's a couple questions on part C3. Somebody just want to quickly type in what they were combining or what was the first part of it. Otherwise, I gotta go kind of take a peek at it on a different screen. What were they combining there in part C3? Water and calcium. Yeah, so water and calcium also would be a single replacement. And the way you could kind of think about water in that case is like so. Although we think about water kind of like H2O as together, in that particular case, you can kind of think of like water as H and OH, almost like H plus and OH minus. So when it reacts with calcium, which again in this form does not have any charge, but when calcium does get a charge, it's going to be positive. So it is going to be a single replacement reaction where it will go and actually kick out the hydrogen. And as we just talked about up there and right here, when it kicks out, right, that's where you should get your hydrogen gas, which should have been some bubbles that you saw. And then what you're going to get, and I'll let you finish that second part here, is you're going to get calcium, which will gain its normal charge of +2. And you think this side. So you put those for your second guy there. So water's kind of weird like that. It will sort of look like you kind of think of it as H plus and OH minus. And I think we saw a little bit of that when we were talking about periodic trends. We saw those videos with like the lithium in water, the calcium in water, the potassium in water. And if you remember, a lot of those guys would sort of ignite or catch on fire. And they would catch on fire because they're basically producing H2, and the heat and stuff like that would catch it on fire. Yeah, so just like I had it there, you could pretty much put them together like that if you like. Sometimes people might put the calcium and the oxygen together and make calcium oxide, but really what you probably have in that situation is the calcium and the hydroxide coming together, and it will turn basic. Yeah, I think they replaced that one, so they might not have updated the. The question was, I think in E3 they showed copper 2 sulfate instead of mercury 2 mercury 2 nitrate. I think they might have replaced the mercury to get rid of the mercury when you physically would have done it. So you could just cross it out and use whatever they use in the example on the video. So if they use the copper 2 sulfate, then you could use that instead of the mercury nitrate. Yeah, water, it does have a positive and negative side when we're talking about in terms of lecture. And in terms of lecture and all that, when we look at water, it really is a covalently bonded compound. So they're sharing electrons and stuff like that. Um, so the hydrogen side is more positive because it's a polar molecule. Oxygen is more negative, and that's what we're talking about, a positive and negative side of water, because it's basically a polar molecule, like we were talking about in bonding. Now, in this situation, this is just a way that you could kind of think about it in these type of reactions, especially like a single replacement reaction, for example, that involves water. And a lot of times with acid base sort of chemistry, um, we think of water almost in the terms. The application of how water sort of reacts is sometimes thought of more as like an ionic compound, even though it's really not an ionic compound. I'm not sure off the top of my head, Brianna, but I believe probably if you're getting towards the end of those reactions, those are double displacement reactions, like what we were talking about in lecture. So if you, let's go, let me get a new page here. So again, if you look at any type of equation or reaction and you basically have two things that are ionic, so you can recognize them as sort of a positive, negative guy. What's always going to happen in those is just they're going to switch partners. So again, that positive A will then connect with the negative D, and that positive C will connect with that negative B. And what it will form is two new ionic compounds. So again, the key is if you're trying to predict what's on this side, you want to just get the right formula first. And then balance it. So second, balance the equation. Don't try to do those things together. Otherwise, again, you will probably end up with the wrong formulas on the product side. Yeah, so for part B, again, that's basically what's known as electrolysis of water. I think I got it on this page here. And where did you go? Maybe it's one more back. Look one more back, maybe. There it is, right here. So what's happening there in part B is you're basically running an electrical current over water, causing a chemical change, and it's producing basically two gases, which is your hydrogen and your oxygen. Yes, Brianna, that looks good. It just needs to make sure that you balance it. It would turn out like that. So the aluminum would end up with the iodine, and aluminum is +3, and the iodine is -1. So that will get you Ali3, and then the potassium is +1, and then nitrate's -1, so you will get KNO3. And again, at this point, you now don't want to go back and put those numbers in front to balance it. So I'm not sure, Eric. I think somebody said that they might have swapped out the mercury 2 nitrate with something else, but just in case they didn't, let me go. Let me just find a page to write on. Hang on one sec here. I think this page will work. So you're looking at mercury 2 nitrate. And again, I would check the video, but I thought somebody just said that maybe, excuse me, that they switched it out with something else. So that's mercury 2 nitrate and sodium phosphate. So the sodium phosphate will look like this. Again, mercury 2, which is this, nitrate, which is this, which is again why we need 2 of the nitrates here to start with, sodium, which is +1, and phosphate, which is -3. So why we need 3 of these to start with. So this again, when you look at it, is a positive, negative guy, positive and negative. And that's what we were talking about today. This is your double displacement reactions. So basically what happens is the 2 positive guys will switch partners. So in this particular case, let me just grab a different color maybe. Go green. So in this particular case, what's going to happen is our mercury is going to come over and connect with our phosphate on the other side. So you want to put those together so that it balances. And then the other thing that will happen is the sodium will come over to the nitrate. And again, you want to just this example, if you did nitrate, you can we go 3 here, so the next one, put together the ones. And at that point, you want to go and put in front there to balance out the actual equation. But you do want to start with the first one. And I do think that they might have switched it to copper 2 sulfate, so you might want to double check the video, but I believe on that one, a couple of people have told me that they switched it to copper 2 sulfate. So you should switch it to copper 2 sulfate, which is which looks something like, I'm imagining this is what they use. And again, the copper 2 means it's a copper with a +2 charge. Our sulfate is -2. So when we put that together, we get this formula. Yeah, if you think it would be helpful, do you think I should upload these as well? I probably will. Okay. So they'll probably be up there as well. And again, a reminder, all recordings take a little bit of time to process. So hopefully by the next day or so, it should be up there. You're welcome. So, excuse me. So, great. So that's a certain type of reaction we haven't got to yet, but that's if you look through the introduction as well, it's what's known as a combustion reaction. And typically, on a combustion reaction, if you start with something that's organic, which basically just means it's made up of carbon, hydrogen, or oxygen, essentially, when you react it with oxygen, it will always form these two things, CO2 and water. So carbon dioxide and water. It's basically, for example, the CH4, which is the example. It's basically what happens when you light that Bunsen burner, like we've done in lab. And these are always the products, really, of this type of reaction, which is known as a combustion reaction. And especially one that involves organic, and this is typically the one most people talk about in combustion reaction. There is a more sort of generic definition of a combustion reaction, That basically just means it just needs to have oxygen involved. But I think in this case, in this lab, it typically is that organic I plus the oxygen will always make CO2 and water. So it's usually a pretty safe bet if you see something like that that's organic and O2, CO2 and water is most likely what you're going to get there. Yeah, especially really, and that's usually what people are talking about in terms of a combustion reaction is the one that involves the organic guys, the car like the CH4, for example. It will always form CO2 and water. There's actually a more general definition of combustion. So, for example, I think we got one up here that we saw earlier. One more, I think. So, for example, I think it might be here. This reaction that we saw earlier, some people will still consider a combustion reaction because it basically has O2 involved. But probably 9 times out of 10, when people talk about the combustion reaction, they're usually not referring to a reaction like this. They're usually referring to like the one that we were just doing there. Where to go? One more. They're usually referring to this reaction here where you form CO2 and water, which I think is what the one in the lab is for today. You're welcome. Yeah. So Eric, the sulfuric acid and sodium hydroxide is really an acid-base reaction. Let me just grab something here to write with. It also could be thought of as a double displacement reaction. So you have H2SO4 plus sodium hydroxide. Although it truly is a acid-base reaction, usually how it's classified, it is also a double displacement reaction, with this being positive, this being negative, this being positive, this being negative. And again, the same thing is going to happen. These two guys are going to switch partners. And what makes up this acid, like we were talking about with acids, is really H plus and SO4 2 minus. Those are the two major ions that make that up. While when we look at sodium hydroxide, it is really made up of sodium plus hydroxide. So again, what's going to happen is this positive guy will come over here. This positive guy will come over here. And that's going to give you the two products that are on this side. So when we take something like this, where we combine H plus and O minus, again, I'll let you do. I want to make sure it's correctly in terms of their charges, and that will get you your other product. Close, Grace. Remember though that when you do write formulas that are ionic, when you write the formula, it should always be the cation or the positive guy first, and then the anion. So what you got there, you just need to switch it around. The sodium should come first, and then the sulfate should come second. But you are correct, you do need two of the sodiums there to balance it out. So it should look something like Na2SO4. Okay, everybody, I think this is towards the end of our normal lab period. So I hope this was helpful. This will be my anticipation as to how most of the lab periods probably will be. You could, again, use this time wisely to try to work on those. You get your questions answered and everything. A reminder, well, that again, when you're done with the lab, make sure that you do upload it on the Canvas site in the assignments. Um, and if you can, try to make it all one file, that would be great, and upload it. We will resume lecturing on Wednesday at our normal time, and we'll do kind of the same situation here. Um, and again, a reminder that the exam will be next week on our normal topics that were going to be covered on that exam. And if you have any questions about anything or need to contact me outside of this time, then obviously, obviously you can use my regular email just like normal, and I'll get back to you. Other than that, if you're all good, have a good rest of your day. I'll see you all probably on Wednesday. Uh, Take care.